Hello, today we will talk about SI unit, base and derived unit. You remember we talked about the basic idea of base and derived unit. In mechanics, we have three base quantities. They are length, mass, and time. And for the length, uh, base unit is meter, and the mass has a kilogram unit, whereas time has second unit. Second. So we need to define how long 1 second is, and how long 1 meter is, and how heavy 1 kilogram is. So for the 1 second, it was defined based on the rotation of the Earth. Uh, so you know, 1 day is 24 hours, and the 1 hour is 60 minutes, and 1 minute is 60 seconds. Then we can see that 1 second is 1 over 86,400 of one solar day. But this one is a little bit not that precise. So now we are using the atomic clock. The atomic clock is based on the vibration of cesium atom. And then we define 1 second is time required for 9,192,000,000 and 631,770 oscillations. So that's the 1 second. And nowadays, this atomic clock, the technique is more advanced, so we can determine 1 second into the accuracy of 10 to minus 20. So we can measure the time very accurately, and GPS did that kind of precise time definition, precision. For 1 meter, it was defined in 1791 as 1 over 10 millionth of the distance from the equator to the North Pole. Notice that people knew how to determine the distance from the equator to the North Pole in 1791. So it is more than 200 years ago. So as I see this definition, I'm kind of amazed that 200 years ago people can travel from the equator to the North Pole, and then they can, you know, measure the distance. But this definition is not that convenient and not that accurate. So based on this definition, people made a platinum iridium bar, and this standard meter bar is in International Bureau of Standard, the Paris. But still, this standard meter bar has some uncertainty. So in 1960, people redefined 1 meter in terms of the wavelength of the light. And according to this definition, 1 meter is equal to 1,650,000,000 and 763. Oh, sorry. 1,650,000 and 763.73 wavelengths of orange light emitted by krypton atoms. So the accuracy of 1 meter is here can be up to minus 10 to minus 10. And then people note that we can do better. In 1983, they defined 1 meter is the distance light travels in a vacuum in 1 over 299 million and 792,458. Here, let's say we can measure the distance that light travels. So 1 meter is the distance light travels in 1 over this number. This is the speedable light in vacuum. So here speedable light in vacuum is constant. This is constant, but 1 meter is the speed multiplied the time. So we can measure the length with the accuracy of time. You remember using the atomic clock, you can measure the time very accurately. So we can have that accuracy for the length. For the kilogram, we don't have a precise definition. Currently, we are using the mass of a platinum iridium cylinder, kept at the international bureau of weight and measures via Paris. So unlike the length and the time, we don't have a very precise definition of a kilogram. So now people are trying to have a new mass standard, and I think this is not completed yet. So I want to mention that there is a movement that we had better define the mass based on other fundamental unit. We use some prefixes. For instance, 10 to 15 is called the peta. 10 to 12 is called the tera. 10 to 9 is called the giga. Whereas 10 to minus 15 is called a femto, and 10 to minus 12 is called pico. And as you may know, 10 to minus 9 is nano. You remember we have metric system, but there are other systems. So we need to know to convert the unit in different systems. To convert the unit, we need a conversion factor, which is a ratio that expresses how many of one unit are equal to another unit. For instance, 1 kilometer is 1,000 meters. So 1 kilometer divided by 1,000 meters is 1. This is called conversion factor. So if you want to express 80 meters in terms of kilometer, then we multiply 80 meters by a conversion factor. 1 kilometer divided by 1,000 meters, then meter unit is cancelled, so we find 0.080 kilometer. So we can convert the unit from meter to kilometer. And then for the conversion factor for the time is 1 minute divided by 60 seconds. For instance, let's say this is the velocity. I think it's not very important, so yeah, that's the conversion factor for the time. And for the conversion factor for kilogram and gram, we have this 1 kilogram divided by 10 to 3 grams, so we can convert to the mass unit. Let me move on to section 1.4, dimensional analysis. You remember physics is based on measurement, and we measure physical quantities, and we define the dimension of physical quantity is its dependence on base quantities. You remember in mechanics we have 3 base quantities: length, mass, and time. So for the volume, you know that volume is the square of the length, so we say L cube. For the base quantities, for length, we use symbol L. For the mass, we use symbol M. For the time, we use symbol T. So for the speed is length divided by time, so we say L over T, or L times T to minus 1. So that's the dimension of physical quantity. And then the importance of concept of dimension is any mathematical equations must be dimensionally consistent. And then from the dimensional analysis means we compare the dimensions of the equation to check whether that expression is correct. So here it says that determine whether an equation involving physical quantities is dimensionally consistent. That is called dimensional analysis. Suppose you are not sure about the formula for the area of a circle. You think that it may be pi times r square or 2 pi r. So you are not sure which one is correct. Then we can compare the dimension of the area of a circle and these expressions. Let me calculate the dimension of area. That is L square. You know it. And then for the formula, pi r square, pi is a constant, so it doesn't have dimension, so it is 1, you can say. So here r has a dimension L, so pi r square has a dimension L square. And then 2 pi r, 2 pi is constant and r has a dimension L. So 2 pi r has a dimension L, whereas area has a dimension L square. So you can see that pi r square should be the correct formula. Okay, I think today this is good enough. If you have any questions, please send me an email, then I'll answer the questions. Thank you. Bye.